For example, Msloub and Bouziani in 1999 looked into the following problem. They considered this equation where Q is 0R times 0T and F, phi, psi, small m, and mu are given functions. They established the existence and the uniqueness of a strong solution. In 2002, also Msloub and Masoudi proved the existence and uniqueness of a strong solution of this problem. They considered this equation with these conditions, where Q is 0L times 0T, and big F, phi 1, phi 2, E1, and E2 are known functions. Recently, Al-Hazani and Msloub in 2023 looked into the following pseudo-hyperbolic problem, where G is 0 mu times 0 T, delta is a strictly positive constant, and R, this R, and its derivative satisfy some specific conditions. By using some a priori estimates, they established the existence and uniqueness of solution. In 2024, Al-Hazani et al. Considered the following two-dimensional fractional parabolic equation with Neumann and no local boundary conditions, where D is 0A times 0B, and sigma between 0 and 1, and the function H satisfies these conditions. They proved the well-posedness of the problem by using the energy method. Now, I state some preliminaries needed for the proof of our main result. We consider this problem. We have a system of two hyperbolic equations with one control and with Bessel operators. We suppose that the function u and v satisfies this condition. This one is an integral condition. Also, we suppose that u and v satisfy these initial conditions. Here, alpha and a are positive real constants, such that alpha satisfies this inequality. And U0, U1, V0, V1 are given data. Our main result here is to show that the unique dissipation is strong enough to stabilize the system, at least on a polynomial rate. Now, we need to define some operators. So for any function v in L1, we set lambda v equals the integral between 0x vs ds, and lambda eta v is the integral between 0x the eta v eta d eta. We also denote by L2x the weighted L2 space with the norm, this norm. So let V0x and V1x be the Hilbert spaces equipped with inner products respectively, the first one and the second one for V1x, and with associated norms. This for the norms with V1x. Next, let's be also the Banach space consisting of functions u endowed with the following norm. And let H be the Hilbert space, which consists of functions f with the following finite norm. Our problem can be written in the following form, where L is an operator defined by this. L1 is L1, small L2, and L2, big L2 is L2, small L1, and L2. And the domain of the definitions of this operator is the following. So we define let's be L bar. In this work, we considered this system of two hyperbolic equations with Bessel operators and one control. We suppose that the functions u and v satisfy these conditions and these initial conditions. We suppose also that alpha and a are positive real constants such that our alpha satisfies this inequality and u0, u1, v0, v1 are given data. In this work, we show that the unique dissipation is strong enough to stabilize the system at least on a polynomial rate. Now we start by defining these two operators that define lambda v for every v in L1. We define lambda v x equals the integral between 0 and x, the vs ds. And lambda eta v is the integral between 0 x, eta v eta d eta. We also denote by L2x the weighted L2 space with the following norm. And we consider the following two spaces, V0x and V1x. They are the Hilbert spaces equipped with respectively inner products, this for V0x and this for V1x, and with associated norms given by this and this. Next, let B be the Banach space consisting of functions u in L2 0t infinity 0t L2x endowed with the following norm. And let H be the Hilbert space which consists of functions capital F with the following finite norm. Our problem can be written in the following form, where L is the operator defined by this, is L1 and L2, and L1 and L2 are given by this formula. And capital F is F1, F2, where F1 is this and F2 is 0v0, v1. The domain of our operator L is given by this formula. So we define the closure of the operator L bar, and we consider the L bar is the domain of L bar. A solution of this equation is called a strong solution of our problem. In a standard way, by using the energy method, we can prove the following result about the existence and the uniqueness of a strong solution of the problem in consideration. For any u0, v0 in v0x and u1, v1 in L2x, there exists a unique strong solution of our problem. Now, in this part, we introduce several functionals and establish various related lemmas. We start by introducing the energy functional E1 associated to our problem. We defined E1t by this formula. This is E1. The first lemma is under the condition that alpha satisfies, we have our energy functional is positive. Now, by multiplying the first equation in our system by this formula, and the second one by this, and using integration by cuts over 0, and we get in a routine manner that the derivative of the functional E1 satisfied is negative because A is positive. So our energy is decreasing. Now we consider the functional phi t defined by this. And we can prove that this functional phi satisfies along the strong solution of our problem the following formula. That is, the derivative over our phi equals this formula. Now we define the second order energy functional by E2. E2t equals this formula. We can also prove that the derivative of E2 equals minus A times this integral. So E2, derivative of E2 is negative, and E2 also is decreasing. Now we consider the following functional psi defined by this. We can prove also that this psi satisfies along the strong solution of our problem in consideration satisfies this formula. The derivative of psi equals this formula. Now, we can prove that there exists strictly positive constants n, epsilon, and small m, such that this functional big F equals n times E1 plus E2 plus epsilon phi previous functionals plus psi. So these functionals satisfies along the strong solution of our problem. The derivative of this functional is less or equal than minus small m times E1 for all t positive, where this small m is positive. We can use this result to prove our main result, in which we obtain that the energy functional E1 defined by 9 satisfies for some k positive that the E1 dt of t less than k over t for all t. That is, our energy functional is decreasing, and the type is polynomial type. Now we finish, and that was what I want to share with you. And I finish this talk by giving some references about that lies about this work. And thank you very much.